Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Fabry-Perot Interferometer, its principle, experimental setup and working. Let's begin. Fabry-Perot Interferometer was devised by two French physicists, one Charles Fabry and Alfred Perot, in the year 1899. It differs from Michelson interferometer and contains plane surfaces which allow multiple rays of light to produce sharp interference pattern. It acts on the principle of multiple reflection from a partially reflecting and partially refracting surface to obtain interference pattern. Let us proceed towards experimental setup. The basic setup of the Fabry-Perot interferometer possesses the same general principle of Michelson interferometer. An extended source, the extended source, light waves are emitted the extended source rays of monochromatic light with a collimating lens which makes the extended light parallel. That is a collimating lens these rays are parallel. Let me take one of the ray, two glass plates named as P1 P1 and P2. These are the glass plates which are arranged parallel to each other. These two plates can be made up of quartz also. One plate is polished highly to make it completely reflecting, whereas the other plate is partially reflecting and partially transmitting. The ray coming from this here reflection, that surface is entirely reflecting somehow, the transmission. Next, here reflection and transmission. Reflection and transmission, and so on. In between these two plates, a thin film is formed, and that film contains air between the plates. The multiple reflections take place in this thin film, which causes the interference pattern, and the thickness of that air film can be measured by changing one of the glass plate as fixed and another glass plate is movement with respect to the fixed one. Here we use a achromatic focus lens achromatic focusing lens that uses to focus the rays so as to avoid the chromatic aberration. Here we place a screen dash dash. These rays are focused at that point having achromatic aberration. No chromatic aberrations will be there. And here we observe the interference pattern just like circular rings. Alternate dark and bright fringes are obtained due to the internal reflection in between these two glass plates, which act as thin air film. And that screen STS, where the fringe pattern consisting of alternate bright and dark circular fringes with center on the optical axis is formed. This one is the experimental setup of Fabry-Perot interferometer. Now we proceed towards theory and working. That will be the experimental setup. Now theory and working. Two parallel glass plates named as P1 and P2. Here is the source S at an angle theta. The light is incident here. Let point be A1. That ray reflection and transmission, as that surface is entirely reflecting, that one is partially reflecting and transmitting one. At point B1 named as T1, named as A2. We take that ray as R2. Here the reflection, it may be R1. Here transmission and reflection. B2, B3. Let you take the plane light ray of unit amplitude incident at an angle theta on the glass plate P1. Let a plane light ray of unit amplitude incident at an angle theta on the glass plate. P1. The extended source S allows the light to fall on that of plate P1 at all angles on the plate. A set of parallel reflected rays as A1 R1, A2 R2, A3 R3 and a set of parallel transmitted rays as B1 T1, B2 T2, B3 T3 are obtained due to multiple reflections between these two plates P1 and P2. Let us prefer the reflection coefficient of amplitude. Let the reflection coefficient of amplitude under root of R and transmission coefficient of amplitude is under root of T. Reflection coefficient of amplitude under root of R and transmission coefficient of amplitude is under root of T. Unit amplitude, here we have taken the amplitude of incident ray RA1 as unit. So, the amplitude of ray A1 B1 becomes under root T. Here transmission takes place, that is amplitude 1 Therefore, at the top surface we take transmission, the amplitude under root of t. The amplitude of ray B1 T1, due to that ray here transmission occurred. So, root 2 root t into root t is equal to t, that will be the amplitude here. In this way, the amplitudes of ray B1 A2, due to that ray here t under root of t, and the process is reflection, here under root of t into under root of r, that is t into r, that is under root of rt. Again, at that of case A2 B2, due to that ray here rt under root into reflection under root r is equal to r under root of t. Next, at that of surface reflection r under root of t, here transmission occurred into under root of t, here we obtain rt. At that of case due to that ray, so r under root of t into here reflection under root r. Next, for that purpose we have r under root of t into under root of r into under root of r, it will be r square under root of t. Here r square under root of t into under root of t, which is equal to r square t. Like this it proceeds, here t, rt, r square t, r cube t, like that. In this way the amplitudes are classified. Now, we take the refractive index of air. Within P1 and P2 air will be there, so the refractive index of air is 1. There is no phase change due to reflection from that of silver surface, means the reflection from rarer medium, no additional phase change, or we can say no additional path difference is introduced here. So, we write that one. Now, as the refractive index of air is 1, which is the rarer medium, and there is no phase change due to reflection from rarer medium. Let us calculate the path difference between two conjugative transmitted waves. Therefore, the path difference between the two consecutive transmitted waves is this 2 mu t cos theta, which is equal to 2 t cos theta, as mu is equal to 1 for air, that is the path difference delta. Hence the phase difference, therefore the phase difference phi 2 pi by lambda into path difference 2 pi by lambda into 2t cos theta or phi is equal to 4 pi t cos theta divided by lambda. So, the displacement of that of incident ray now the displacement of the incident ray is given by y is equal to a sin omega t. Here the amplitude is 1, that is equal to sin omega t, as a is equal to 1. Similarly, the displacement of transmitted ray, similarly the displacement of the transmitted ray here y1 its amplitude as t sin omega t, y2 amplitude rt and phase omega t minus phi. Similarly, y3 r square t with amplitude r square t, here sin omega t minus 2 phi, successive phase angle change, and y4 rq t sin omega t minus 3 phi, and so on, that proceeds and so on. So, these waves, the amplitude of these waves are superimposed with each other. Then we apply the principle of superposition. Let the resultant amplitude the amplitude of resultant wave obtained using principle of superposition. B, let A be the resultant amplitude and the resultant phase difference be delta. This is the resultant amplitude, that is the resultant phase difference. Now, therefore, the displacement y is equal to resultant amplitude A sin omega t minus resultant phase difference del. According to principle of superposition, y is equal to y1, y2, y3 dot dot dot. Substituting the values here, therefore y as a sin omega t, a sin omega t minus delta is equal to y1. The values of y1, y2, y3 are putted. T sin omega t plus RT sin omega t minus phi plus R square t sin omega t minus 2 phi plus dot 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 sin A minus B sin A cos B minus cos A sin B is equal to T sin omega t plus RT sin A minus B sin A cos B minus RT cos A sin B, again sin A minus B plus R square T sin A cos B minus R square T cos A sin B. Now, we have to equate the coefficient of sin omega t and cos omega t on both sides, equating the coefficient of sin omega t and cos omega t on both sides. We get, let we equate the coefficient of sin omega t. Here we obtain A cos delta, A cos delta is equal to T plus RT cos phi, RT cos phi plus r square t cos 2 phi, r square t cos 2 phi, and so on. And equating the coefficient of cos omega t, here you obtain minus a sin delta. Again at that side also minus term, so minus term in both sides are cancelled with each other. We have a sin delta is equal to rt sin phi plus r square t sin 2 phi plus dot dot dot. As we know, the resultant intensity I is the square of resultant amplitude. I is equal to a square. That a can be written in the complex form as a e to the power I delta into a e to the power minus I delta. There will be no such change. So, a e to the power I delta, here I is equal to under root of minus 1, we read it as iota. E to the power I delta as cos delta plus I sin delta, e to the power minus I delta cos delta minus I sin delta. Let we evaluate the terms as a cos delta plus Ia sin delta, a cos delta minus Ia sin delta. Evaluating the terms a cos delta plus I a sin delta, Ia sin delta, which is equal to, put the values of a cos delta and a sin delta here, t plus rt cos phi plus I sin phi, taking rt as common, plus r square t cos 2 phi plus I sin 2 phi plus dot 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 is equal to t plus rt e to the power I phi cos phi plus I sin phi, that is e to the power I phi plus r square t, here e to the power I 2 phi plus dot dot dot. Taking t as common, we have 1 plus r e to the power I phi plus r square e to the power I 2 phi plus dot dot dot. That is the expansion of 1 minus r e to the power I phi to the power minus 1. When we expand the terms, So, we obtain that series. Now, T divided by one minus r e to the power I phi. Similarly, when we evaluate a cos delta minus I a sin delta, what we obtain? Similarly, a cos delta minus I a sin delta is written as T divided by 1 minus r e to the power minus I phi. Let the intensity is calculated. Put these evaluating values. So, the intensity is obtained. Thus, intensity I is equal to a cos delta plus I a sin delta, its value T divided by 1 minus r e to the power I phi, T 1 minus r e to the power I phi. Again, the value of a cos delta minus I a sin delta is T divided by 1 minus r e to the power minus I phi. Here T square, its multiplication as 1 minus r e to the power minus I phi. When 1 is multiplied to that term, then minus r e to the power I phi minus minus plus r square e to the power I phi e to the power minus I phi, that is 0. Here T square divided by 1 plus r square, here r as common minus r as common, inside that bracket we have e to the power minus I phi plus e to the power I phi. T square divided by 1 plus r square minus r, putting the value of e to the power minus I phi plus e to the power I phi. Let me evaluate it here. E to the power minus I phi plus e to the power I phi. E to the power minus I phi as cos phi minus I sin phi. E to the power I phi as cos phi plus I sin phi, minus I sin phi plus I sin phi cancel out. We have 2 cos phi minus r 2 cos phi. T square divided by 1 plus r square minus 2 r. Here cos phi can be written as cos 2 phi by 2. There will be no such change. The value of cos 2 phi cos 2 a is equal to cos square a minus sin square a. If we write it in terms of sin, so cos a can be written as 1 minus sin square a minus sin square a, here 1 minus 2 sin square a. So cos 2a in terms of sin can be written. So t square divided by 1 plus r square minus 2r cos 2a as 1 minus 2 sin square a, 1 minus 2 sin square phi by 2. t square divided by 1 plus r square minus 2r plus 4r sin square phi by 2, 1 plus r square minus 2r, that is the square of 1 minus r whole square plus 4r sin square phi by 2. The expression for resultant intensity I. That expression represents the resultant intensity which express the resultant intensity and depend upon r and phi, depends on r and phi, that is coefficient of reflection, reflection coefficient and phase difference phi, that will be the resultant intensity depend upon r and phi. Then the condition for maxima, for maxima that denominator term must be minimum. So, I be maximum value. The condition when denominator is minimum, we obtain the maxima, the minimum value of sin theta or sin square phi by 2 will be 0. For maxima, for maximum intensity, sin square phi by 2 will be 0. Therefore, phi by 2 is equal to pi, 2 pi, 3 pi, like this, generally which is n pi. Therefore, phi is equal to 2n pi. When the phase difference is equal to integral multiple of pi, then we obtain maxima. Then for minima, for minimum condition, for minimum intensity, that denominator must be maximum. The maximum value of sin is 1. So, sin square phi by 2 is equal to 1, or phi by 2, that is 2n plus 1 pi by 2 or multiple of pi by 2, or phi is equal to 2n plus 1 pi or multiple of pi. Then we obtain the minimum intensity. And the condition for maxima, or the condition for bright fringe, path difference is integral multiple of lambda, n lambda. Path difference here 2t cos theta is equal to n lambda. Here we take mu is equal to 1. Here mu is equal to 1 for air. In between these two plates, the medium is air. Again, condition for minima, path difference odd multiple of lambda by 2, 2n plus 1 lambda by 2, or 2t cos theta is equal to 2n plus 1 lambda by 2. That will be the condition for minima or destructive interference or dark fringe. Look at these expressions. So, the angle theta is constant for particular values of n, lambda and t. So, the locus of all points having the same values of theta. Therefore, we obtain a circle. So, the fringe as we obtained here just like circular rings. So, with the help of this video lecture, we understand Fabry-Perot interferometer principle, experimental setup, theory and working. We obtain intensity, condition for maximum intensity and condition for minimum intensity, and condition for maxima and condition for minima. So, with this useful and informative notes, let me wind up these sessions. Thank you.